Hi. So, I guess I'm a paleontologist. I'm more of a palaeoceanographer, micropalaeontologist. I work in the geography department, so just be nice to me. And also, deglacial and Holocene, so I'm not sure how you feel about that as fossils, but I count them as fossils. So I'm going to be discussing some work I've been doing as part of my PhD at the University of Nottingham, working on marine sediments from South Georgia. So South Georgia is a tiny little island in the middle of the Southern Ocean. So I'm working on a couple of marine cores that have been collected from the shelf in 2012 by the British Antarctic Survey on this beautiful ship, the pre-Boaty McBoatface. Really nice boat to sail on. I'm not sure why they were replacing it, but I think it's coming to the end of its life. So I'm going to introduce kind of what my project's about, and then I'm going to talk about some of the results that I have so far, and a little bit of interpretation, which is kind of still being developed. So if anyone has any ideas, I'd love to hear them. So the first thing to say is, why South Georgia? So the location of South Georgia, right in the path of the Antarctic circumpolar current, means that it's ideally placed to kind of investigate any changes in this current, and also its position between Northern Hemisphere climate zones and Antarctic climate zones. Means if these fronts are moving, you should hopefully get a change in the signal recorded in the sediments on South Georgia. In particular, it's very interesting because the southern this front here, the southern ACC front, wraps around the island and generates this huge phytoplankton bloom here. This is one of the biggest carbon sinks in the Southern Ocean, and so maybe really important in terms of these transitions between glacial and interglacial cycles. So you could be dumping a lot of carbon dioxide into the ocean here and potentially releasing it if this shuts down as well. So because you kind of have this paradox in the Southern Ocean where it's really high in nutrients, but it's very low in chlorophyll, so you don't have this productivity, except for where I think it's mainly to do with like limiting nutrients. So here, because the current's interacting with the shelf, you get the iron fertilising this big bloom. So it's quite important in terms of understanding paleoclimate. So what am I doing to try and understand these processes? I'm using a multiproxy approach, so stable isotopes, sediment properties, biogenic silica, alkanones to try and get a temperature record, and of course benthic foraminifera. This is what I'm going to focus on in this talk, because that is obviously paleontology, kind of. And this is why I got into this PhD, because I really love foraminifera. They're so beautiful, so diverse, all these different forms, but also they provide a lot of information, paleo-environmental information. So you've got things like paleoproductivity, oxygenation, current velocity, temperature, salinity, and of course, as I mentioned in the other slide, there's geochemical properties that are stored in their calcareous shells. So there's a real diversity of information you can get from them. So I'm just going to talk about the assemblage work really. So these are all the species that I've identified during the taxonomic work that I've done, and you can see that the diversity of forms is quite incredible, really beautiful things. And I'm just going to pick out some of the important taxa that we'll be talking about later on in the talk. So this is Fersenquina fusiformis, which is a phytodetritivore, really tiny little thing, but it can be present in huge abundances. These two are Miliamina, so they make their tests from little bits of silica. So they're not calcareous, they're agglutinated foraminifera. And then this is another assemblage, which these are the kind of more dominant and this more mixed assemblage. So I have all this data, and then plotting it down core, you obviously end up with a very complex plot. You can maybe see, so that's the Fersenquina. It looks like it's more abundant in the base here, in the deglacial into the late Holocene. Then these Miliamina seem to be more abundant in this mid to late Holocene period, and then a more diverse assemblage in these other areas here. But to go beyond just identifying them visually, saying these are the different assemblages, putting lines between these zones, I tried to apply some statistics. So done a little cluster analysis, and it seemed to be a couple of decent groupings here for the Miliamina and for the Fersenquina, these groupings. But then the rest of the samples they don't really group together, they're quite sort of split up. So I went to further test those groups and see if I can group the other samples. I did a detrended correspondence analysis, and you can see the groups they plot out quite nicely, and then the rest of the samples plot in this one area here, and there's not really any overlap in the groupings, although you can see that the 95% confidence there is a bit of overlap between those two groupings. and here as well. But kind of where the samples plot, they don't seem to mix. So that seems to support the idea that these assemblages are robust. And then I did a further, so there you can see the different assemblages. Did another DCA just on the milliamina, and potentially 2 further groupings in here. So milliamina elandii sub-assemblage and then the lata. Obviously there's quite a lot of overlap, and the groups they're not hugely separated. So using those groupings, I was able to look at how the assemblages vary downpour. And so you can see this darker green colour is where you have the Fersenquina fusiformis assemblage really dominating in the deglacial, and then reappearing a little bit later into late Holocene. And then you have this more mixed assemblage, which I call the Astrononion Cassigelinoides assemblage. Those are the 2 key components of that assemblage in the early Holocene, and then returning right in the late Holocene. But then, you get this period during the mid-Holocene and into the late Holocene, where you have this milliamina assemblage dominating the record almost entirely. So now I'm going to discuss what these assemblages might mean in terms of the ocean conditions at the time. So, looking at the Fersenquina assemblage, in the very base of the core, you have 3 meters from this 8-meter core, which represent just 600 years of the core, where you've got really rapid sedimentation and these laminae forming. So I think this is probably analogous to something that you find in Antarctica, where you get these carving re-entrant bays. So as the ice sheet's retreating, where there's troughs coming across the shelf, you get the warm water flows up underneath the ice and then melts these carving re-entrant bays, which then become a focus for productivity, because you have all the glacial runoff washing into there, triggering this really, really high productivity. And that's where you get these laminae, which are almost entirely Catossauro-style diatoms. And then obviously you've got a lot of erosion material running in between those balloons. So that's what I believe is happening for this really short period. What we find is that so that's supported by other proxies. So the amount of the carbon accumulation rate, the biogenic silica accumulation rate, although not really evident in the isotopes at all. There's no kind of signal for productivity there. But then we have a second phase where it's no longer laminated, and you don't really see this high productivity in the other proxies. You still get the benthic forum accumulation rate is still high, but the other proxies, there's not really that much evidence of high productivity. So it's mainly based on the Fersenquina abundance that this is still a high productivity period. And what I think is happening here, it's to do with the position of this front and how it changes. So during the Holocene and now, the front kind of it kind of interacts with the shelf, but it's not coming right onto the shelf, so you're not getting upwelling onto the shelf. But during the deglacial, the southern hemisphere westerlies, which drive this front and affect its location, are more shifted more equatorward. So the front is interacting onto the shelf and bringing up this nutrient-rich upper continental deep water, which is then triggering this higher productivity on the shelf. And then, so moving on to the milliamina period. So you'll note here that the number of milliamina actually stays fairly consistent throughout the core. It's just the percentage that it really dominates, which suggests that rather than this being a true record of the assemblage at this time, it's actually a dissolution assemblage. So something's happening. These are really corrosive to, really resistant to corrosion. So they're not calcareous. They don't dissolve in acidic waters, and they're more resistant than other agglutinated taxa, which have an organic cement. They seem to have a silica-based cement. So they're very, very tough little critters, and you can't really get rid of them. So I think what's happening here is this is a dissolution assemblage. So the question is, what's happening? Why are we getting this dissolution? What we find is that there's a real slowdown in sedimentation. So this is the age model. Here you see this is that period there, and the sedimentation rate has dropped right down to sort of less than 1 centimetre a kiloyear. So I think what's happening is that as the sedimentation rate drops off, the foraminifera being exposed to more corrosive bottom waters for longer periods of time, you're losing that calcareous element of the record, and you just end up with these agglutinated resistant taxa. Why is that happening is a bit of a mystery, because it's weird. You get a lot of really coarse material. You get this peak in sort of IRD at this period here, and there's also a record for re-advance of the glaciers peaking at this point on South Georgia. So somehow maybe it's linked to that. But what I've found is, so I've generated using alkanones, I've generated a sea surface temperature record for that through the Holocene, and found that there's actually a peak. It's like a degree higher here. So potentially that's linked to maybe higher precipitation changing the glacier mass balance, somehow that's linked to the sedimentation rate. The alternative is this increasing temperature melts the glaciers and that increases the erosion, increasing the coarse fraction. But it doesn't explain why we lose the finer fraction. So something's going on the shelf to increase erosion, like winnowing of the finer sediment. I'm still trying to figure that out. That's the chapter that I'm supposed to be writing right now. So yeah, I think that might be a bit quick, but thanks for listening, and any questions?